Right, so I'm going to start doing a series of mathematical explanations from our website. And I'm going to start off with what I've been working on this morning, which is a party game. It's called Mafia, or Werewolf. They're completely the same game, and they just have different names on top of them. And I'm going to be playing a slightly simplified version of it. So the game works where there are good people and there are bad people, and you know what allegiance you have yourself. And I'm going to start with a 4-player game. So in this scenario, we're going to have 3 good people and 1 bad person. So we're going to have good, 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 bad. The game is divided into night phases and day phases, and they alternate, starting with night. Again, there are different ways of playing this, but they all collapse down into each other. They're all just out by 1 number. And what happens in the night phase is the bad person decides who they want to kill. So it doesn't really matter in this scenario, the bad person is going to kill 1 of the good people. Every day phase, which follows the night phase, there's a vote, and all the people with simple majority can vote to lynch 1 of the people. So in this case, the good people, if they suspected this person was bad, could vote. There's 2 of them, which would be in the majority of the 3 people, and they could get rid of the bad person. However, they don't know who the bad person is, and it could be that they're convinced that this person, number 1, is a bad person, in which case this person would vote for them, and the bad person would vote as well. The good people win the game when all the bad people are gone. The bad people win the game when there are the same number of bad people and good people. And so in this case, and in all the ones I'm going to do today, there's going to only be 1 bad person. So the bad people win if they can get the good people down to only 1 person. So, after the first night, where 1 of the good people dies, we have a couple of different scenarios. Either they lynch this person, or this person. If they manage to lynch the bad person, then they're going to win, because there are no bad people left, but that's only a 1 in 3 chance. 2/3 of the time, they're going to lynch 1 of the good people, and in that case, there's going to only be 1 good person and 1 bad person left, and so the bad people are going to win. So, for the 4-player game, and I'm going to make a notation here, P4 is the probability in the 4-player game that the good people win. And in this case, it's only a 1/3. Which begs the question, what happens in the 5-player game? Incidentally, sorry for all the cuts. I'm just not convinced that I'm in frame every time, so I only perform a couple of minutes of this and then I go and check that I'm actually in frame. So, the 5-person version only adds 1 extra person, so we don't actually have to change that much. So if I rub out that G, we're going to add in an extra G, and we're going to work out the probabilities here. And just while we go along, it's often helpful with solving this sort of maths problem when we're generalising something to build a table of results as we go. So over here I'm going to make a table of results. When n is the number of people, which is in that case was 4, then the P, the probability, is going to be the probability that the good people win, which in this case is 1/3. Okay, right. This game actually has more going into it with the 5-person version. There are decisions to make along the way, and there is a correct decision here. So, just like with the first night phase in the 4-player game, in 5 people, the bad person kills 1 of the good people. It doesn't matter which, it's all arbitrary. Now we go to day 1. Now we have a choice here. You don't have to lynch if you don't want to. If no one can come to a consensus, which is often when you play this game, then you just pass to the next night phase without lynching anyone. And so you have a decision here to make. Is it good to lynch or not? So we're going to break into 2 different cases here. We're going to have one case which is when we're going to lynch, and we're going to have one case where we're going to have otherwise. Okay, so in the otherwise case, we'll do that one first because it's probably going to be easier. If no one is lynched on day 1, then you go straight to night 2. And in night 2, then the bad person is going to kill a second good person. And so we'll be left with 2 good people and a bad person for day 2. But actually we've already done that case. It's collapsed back into the 4-player game. In this one, we know what we should do is try and lynch, and there's a 3rd chance. So if we didn't lynch anyone on the first day, then we've got a 3rd chance still, just like in the 4-player game. So that's what we're going to be comparing our answer to see if it's better or worse. If we do lynch someone on the first day, well, again, we don't have any information about any of these people, so it's either going to be this person, this person, this person, or this person. There's 4 different possibilities. There's a 1 in 4 chance that we're going to lynch the bad person, so there's a 1 in 4 chance that we win straight away, but, that's one way, there's a 3/4 chance that we lynch one of the good people, in which case we're down to good, good, bad, going into the night. But going into the night, the bad person is going to kill another person, and they've now got it 1-on-1, and they're going to win. So there's a 1 in 4 chance we're going to win if we lynched on the first day, whereas if we just waited a day without doing anything, then on the second day, we can win with a 3rd chance, which is bigger. So in the 5-person game, it's actually not worth doing any lynching on the first day, which is slightly counterintuitive. And so it has exactly the same probability of winning for the good guys as the 4-person game. Now we'll add that in. So for 5 people, the best chance we have is a 1 in 3 chance. Is it always 1 in 3? Well, no. And we're going to get better odds as we go along. Right, so the 6-person game. So we've got good, 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 bad. And just as before, night 1, we're going to lose 1 of the good people. So now we've got a choice. Do we lynch straight away, like we did in the 4-person game, or do we wait a bit like we did in the 5-person game? And again, I'm going to lay it out in the same way. So over here we've got lynch on the first day. Over here we've got otherwise. Well, if we do otherwise, then it goes to night 2, and the bad person kills another person, and so we're left with good, 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 bad. But we've already analysed this case. Whenever we do these kind of recursive maths things, we often find that we've already done quite a lot of the work when we're doing a more complicated case. So we've done this one. We already know how to do the 4-person game. It's the equivalent to the 5-person game, because 1 person would have already died in the night. And we know that the strategy here is wait for one of them to go, and then the next day do it. So we already know that this is a 3rd chance. So again, this is the thing we're trying to compare our answer to. If we do lynch someone, well, we've got a 1 in 5 chance of just winning the game straight away, because we've got 5 people left, and we can get the bad person out. But 4/5 of the time, we're going to get one of the good people out. So we'll lynch one of them, and then in the night, another one is going to die, and we're going to be left with good, good, bad, coming in the next day, day 2. But we know this answer as well. We know that if we face this situation in the daytime, then we've got a 1 in 3 chance of winning. Now we've got a bit of a tree developing, and we've done all the branches of it, and we're going to do conditional probability on this. So we've either got a 1/3 chance this way, or the other way, we've got a 1 in 5 chance, or a 4 in 5 chance of getting a 3rd chance. The way we do these kind of probabilities is just a kind of expanding stack. So the probability this way is going to be a 5th plus the chance that we go down this branch, which is 4/5 of a chance of 1/3. So if we can combine that into one thing, we're going to be over 15. So we've got 3/15 plus 4/15, which is 7/15. 7/15 isn't immediately obvious which one is bigger between that one and that one, but in fact this is a bigger number. So this I think is about 0.44-ish. This is about 0.33-ish, and so we've got a kind of clear way that we're going here. This one is the better way to go. So in the 6-person game, we should lynch straight away. And we've got a new result for this. So with 6 people, we've got 7/15. So now the question is 7 people. And actually the logic is very similar. It all just collapses down into the same things. So I'll just rub this off and we'll do another one. Okay, we'll add in another good person. One of the good people is killed on the first night. So if we either lynch someone or otherwise, well, if otherwise, then we lose another person and we collapse down to the 6-player game. And we already know that the chance of that is 7/15. So that's our fallback. On this side, well, if we lynch someone, we've got a 1 in 6 chance of getting them straight away, or we've got a 5/6 chance of ending up with, so we lynch one of them, another one dies in the night, and so we're left with G, 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 B. And we know the strategy for that one is wait a bit, and then lynch on the next day, which is a third chance. So we end up with a very similar conditional probability. It's going to be 1/6 plus 5/6 times a third. So we're going over 18 here. We've got 3 plus 5 all over 18, which is 8 over 18, which is 4 over 9. And again, we have to compare this to this answer. And actually, this number is slightly smaller than this number. So this number, not lynching on the first day, was the answer. With 7 people, we've got 7 over 15. We're choosing the biggest probability from our initial choice. So a third, 7/15, 7/15. We've got 2 hypotheses we can draw from this. One is we've got an odd-even parity thing. The other is that actually there's a more complicated pattern than this. And so after this, once we've done a few cases, we try and edge towards the general case. So we're going to try it with n people. Right, so with n people, it's going to be very similar. So we've got G, all the way up to G, with 1 bad person again. And so in total, we've got n people. So we have n minus 1 good people. On the first night, we lose one of the good people, so we've only got n minus 1 people left now. Same question, do we lynch or do we otherwise? Well, in the otherwise case, we'll have n minus 1 people, and another one is going to die in night 2, and so we're going to have n minus 2 people going into the next day, which just collapses down to the case before. So whatever the probability of the one before is, p of n minus 1, that's what we're going to be comparing against. On this side, we've got a 1 in n minus 1 chance of getting a person straight away. So we've got 1 over n minus 1 chance of just winning the game straight away by getting 1 bad person. Or we've got an n minus 2 chance, so the rest of them out of n minus 1, of getting the wrong person. Then another person is lynched. So the process here is one person was lynched, died in night 1. We lynched another person, which puts us at the same as probability n minus 2, like 2 previous. So the total probability on this side is 1 over n minus 1 plus n minus 2 over n minus 1 times p of n minus 2. And this is the probability of n. But we've actually seen there's an odd-even parity thing going on. So the probability n is either this thing, or it's the same as the probability before it, n minus 1, it's whichever's bigger. Now, I did some proofs earlier. I'm not going to go through the whole induction with you here. What I quite like to do is just show that if n is an odd number, then you should definitely lynch on the first go, that this thing is definitely bigger than this thing. To do the other side of the argument, where it's an even number, it's a very similar argument, but I don't want to make this video too long. I think it's already going to be. So, whenever we're doing odd, even parity things, we've got a useful convention. I think we'll go to a second colour here. So, every time we had an n in the original argument, if we want to signify that n is an odd number, well, even numbers we could write as 2m. So odd numbers we can write as 1 bigger than that. So anytime we saw an n, we're going to write it as 2m plus 1. So if we have 2m plus 1 over there, well, if we replace that by 2m plus 1, we're going to have just 2m there. Over here, 2m, yeah, that's going to be 2m, 2m minus 1, 2m, and then this thing is going to be 2m minus 1, and then similarly on this one. Okay, so we've got a new thing with all of our new subscripts and all of our new numbers written in. And what we want to do is compare this thing and this thing, and we want to decide which is bigger. And there's a common trick when we're doing this kind of thing in mathematics. If we want to compare two quantities to see whether one is bigger than the other, what we do is we define a new variable, so I'll call it, I don't know, y, and it's going to be equal to this thing minus this thing. The idea being, if this thing's bigger than this thing, then y will be a positive number, and if this thing's bigger than this thing, then y will be a negative number. And it's usually easier to check whether something's positive or negative rather than one thing's bigger than the other. So we've got y equals this thing, 1 over 2m plus 2m minus 1, 2m p 2m minus 1, minus 2m. So we need some way of combining these two things here. Because at the moment those probabilities are for different things. This is for the one after this one. At which point I had to look at my notes because it got confusing. This thing and this thing are different, but we have a way of combining them. This thing here we already know the formula for, because again we know the general formula. So, using my notes, this bit here is minus 1 plus 2n minus 2 p of 2m, m minus 1 over 2m minus 1. And now we can combine both of these bits. So we've got this thing minus this thing, sorry for the sloppy notation. We're going to have to clear some space on the board. But, in fact, no, I'm just going to, you can work through the algebra if you really want to. But what it's going to collapse down into is y equals this thing. So we've got p of 2m minus 1 minus 1 over 2m minus 1. And what we want to do is tell whether this thing is positive or negative. Well, this is a probability, so it's between 0 and 1. If we take away 1 from that, then the numerator is definitely a negative number. On the bottom, 2m is just positive, m is defined as a positive integer. And this thing is going to be positive as long as m was bigger than half, which it is, because we defined it 2 as the smallest case. So the denominator is positive, the numerator is negative, and so this thing is less than 0. And so when it was the odd case, this thing was bigger than this thing, and we shouldn't lynch on that day. So on an odd number of people, you shouldn't lynch. Another way of saying that is, even the daytime there's an even number of people, you shouldn't lynch, you should wait a day. But after that, you should start lynching. And the opposite way around, where the proof is very similar, it just goes the opposite way around, is that you should lynch on the first day, and you get something greater than 0 on this. And so we have a general result at that point. Now, you can prove it a lot more formally using induction, if you know how to do that, but actually we don't really need it. Just some general observations here. Firstly, we've only been doing it with one baddie. With two baddies it gets a lot more complicated. You get bigger tree diagrams going on. But actually, it's kind of similar. Also, this pattern here, a third, 7 over 15. If I just read out the next couple, we had... So again, they come in pairs, but the next one will be 19 over 35, and then my calculator just started giving it in decimal. So we had 0.59365. Again, pairs of these things, and it goes in pairs forever. And these numbers seem to be increasing, and an interesting question is, do they increase up to 1? So with 99 good people and 1 bad person, are you going to get a very good probability of winning, or does it tend to some other limit? And I haven't worked on that yet. But work it out yourself. I'm going to be trying to do it.